Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control IIT Bombay. We are almost at the end of the 10th week of lectures on Nonlinear and Adaptive Control, and of late we have been focusing on robustness in adaptive control. It's actually a property that is rather critical for real world implementation, such as the SpaceX satellite orbiting the Earth that you see in my back. So what we were looking at last time was essentially projection based adaptive controllers as one way of implementing robustness. Yeah. So it was a rather nice way. It was sort of a direct attack on the issue of boundedness of parameters, because when there was a disturbance, what we noticed was the bad thing that happens is that the parameters get disturbed. That is, the parameters start to become unbounded. Yeah. And we directly attack this problem by using any prior information of parameter bounds that we might have. And with this knowledge, we use the projection operator using tan hyperbolic functions and show that we can actually design a control law and an update law and filtered variables which are bounded. So everything remains bounded in spite of disturbance. Disturbance does not change anything because of how we implement things. Yeah. So our results are not impacted by disturbance. Of course, in the Lyapunov stability analysis, you still see that uh, you know okay, I apologize, there seems to be a repeat of sheets here. Yeah. So the stability analysis is not impacted except for addition of some kind of disturbance terms in the v dots, and these will essentially result in some kind of residual set behavior, yeah, on the EF. It doesn't matter to us because this is the best expected outcome in case of disturbance anyway in standard Lyapunov based nonlinear control, yeah, or any control for that matter, because there's no way you can counter disturbance using smooth feedback. Of course, you have sliding mode and other sort of non-smooth feedback which can actually do disturbance rejection also, but that's not within the scope of what we are doing in this course. Yeah. So it's a very nice method, right? So very useful. So in fact, let me sort of get rid of this page because this is a repetition of this page. Yeah, if you don't mind, before we go forward. Okay, just a second. Yeah, move to trash. Excellent. So then what we started doing pretty much at the end of the last session was talking about the sigma modification. So we do know that there is a nice solution, which is essentially a projection solution in the presence of knowledge of the bounds of the parameter A, right? But what happens if we do not have, this kind of a knowledge, this kind of a prior information? um, in those cases we have to devise some kind of modifications of the adaptive law. So that's where we started with the standard very simple model we had, and we want to track some xm, and of course we defined an e dot and a standard certainty equivalence control law. With that, we had a standard adaptation law which is well known with a Lyapunov candidate. And what we propose, or what Ianov and Kokotovich proposed in the sigma modification adaptation law, is that you add a damping term. That is, the right hand side had no term in A hat. Right? So this is what we also mentioned in the earlier projection method, that non-certainty equivalence based methods do not have a term in the estimate, parameter estimate in the right hand side of the parameter estimate update log. Yeah, and that's what we do here. You add a term with the A hat on the right hand side, which is a damping like term. So it has a sigma term. So that's why it's called a sigma modification, because they chose the gain sigma here. And gamma is of course retained here as it is. Right? So this is the sigma modification. So we want to start to look at it in more detail today in this session. So I'm going to mark our lecture 10.6. All right. And now uh, we of course add the disturbance, right? I mean, we already had the disturbance in the dynamics, right? And of course the design cannot account for any of this disturbance, so obviously the design remains exactly the same as before, the only difference being the sigma modification. Yeah, so we again take the same Lyapunov candidate. Yeah, so no reason to choose another one, and you get the derivative as E dot minus 1 over gamma A tilde A hat dot as always. Then I substitute for the closed loop dynamics. Yeah, so I substitute this guy here and I get an E dot, which is A tilde X. So this cancels, minus KE from here, and a disturbance from here. Right? So this is what we get, an E dot. And then we have an A tilde A hat dot. And A hat dot is just this. So gamma EX times gamma sigma A hat, and the gamma cancels out. Right? So you're left with EX minus sigma times A hat. All right, great. Now, we continue. So you notice that this EX term cancels this. That's essentially the purpose of the update law. That the update law is chosen so that these two cancel out. So it should not come to you as a big surprise. So once these two cancel out, you have the nice negative term in E. Again, not a surprise. Then you have a term in E and D, which is the disturbance term that we saw anyway in the beginning of this week's lectures. Yep. And finally, you have a term, which is the new term, which is sigma A hat A tilde. This guy. All right. Now, what we do is we write our A hat in terms of the A tilde as A minus A tilde from here. Yeah, so A minus A tilde just from this expression right here. All right, great. And so what happens? You see that I start to get a minus sigma A tilde squared term. Okay. So now I have two quadratic terms, negative quadratics, minus K squared minus sigma A tilde squared. Remember, when we started this discussion on this robustness, I had mentioned that this issue of disturbance causing some states to grow unbounded is primarily an outcome of the fact that we don't have strict Lyapunov functions in adaptive control, right? Even if we start with a strict Lyapunov function for the known case, when we start to do the adaptive control, it becomes a non-strict Lyapunov function because the V dots always come out to be the same as the non-adaptive case, right? But the V had an additional A tilde term, right? So therefore, it became a non-strict Lyapunov, and that was the problem. So this, notice what this sigma modification has done. It has introduced a negative term in the A tilde, and this is what is somehow giving the strictification, if you may. Yeah, this is what is giving a strictification. Of course, this is not for free, because you already had the disturbance term, which was okay. Let's not worry about it. But you also end up with a sigma A tilde A term. So you have an additional disturbance like term here, right? Notice that both these terms are linear in the state. So this is linear in E, this is linear in A tilde, right? A is a constant, unknown, but a constant. Sigma is a constant, and D is not a constant, but it's bounded by a constant. All right, great. So now what do? We use our standard, well, I mean, first of all, we do a norm bounding, right, which is like, this is less than, so I put norms everywhere or an absolute values everywhere because these are scalars. If these were vectors, I would put norms. So this is just less than equal to absolute value of E times absolute value of D, which is less than equal to D max, right? So this becomes the absolute value of E times D max, and then I just put absolute value everywhere, sigma times absolute value of A times absolute value of A tilde. All right, and now I simply do a standard AB less than equal to A squared plus B squared by 2 on both of these terms. Right. Well, I don't do a standard. I actually do something slightly more. Right? So this guy is actually this is written as less than equal to E squared by 2 plus D max squared by 2. So this term is the standard one, but this term I'm writing slightly differently as this is written as sigma is multiplying here and by 2, and then I have epsilon A tilde squared plus 1 by epsilon A squared. Yeah, we already saw this kind of a decomposition also. It's possible because I am simply writing this as equal to A square root epsilon A tilde times A over square root epsilon. Yeah, so this I can do this. This is just a multiplication and division by square root of epsilon. So nothing is changing. So we've already done this kind of a decomposition. So that's what we do for this term. And now you just combine these with the square term, right? Because I have a square term here. So I have k minus 1 half e squared, and then sigma minus sigma epsilon by 2 a tilde squared here. And then I'm left with these square terms in these unknowns, right? So these are unknown square unknown constant, positive constants here. Okay, and then I of course combine this guy and this guy, and I get something like this and something like this. Okay, it doesn't matter. I could have combined it with one or the other and all that mess, but it is sort of irrelevant. Yeah, you would essentially get similar outcomes, similar sort of residual sets. Now, what's happening here, if you notice, is that if you assume k is greater than half and epsilon is less than 2, of course, that's important. Otherwise, these quantities are not positive. So this is just to sort of ensure that you have this quantity positive and this quantity positive. That's all, right? Then we have v dot to be negative semi-definite whenever this is positive and this is positive, and that's given by these conditions. When E is greater than this and also A tilde is greater than this. Now notice what happens, right? What happens here is we get two residual sets. Two residual sets meaning we get intersection of two residual sets, right? So if I was actually to draw a picture, just like we did, for the standard case. So if I was to make a picture like this, let's try. Yeah, and this was say my E axis, and this was A tilde axis. Yeah, this is a rather not perfectly done. Don't worry about it. Let's see. I'm sort of drawing only a projection of this. Yeah, I'm only drawing a projection of this set. So if I draw this guy, so there will be a residual set in E. Which is like this, and then there will be a residual set in A tilde, which is like this. So your trajectories, so it can be very easily shown that your trajectories will in fact lie here. Your system trajectories will in fact lie here. Okay, so this red line of course represents your A tilde, which is A over square root epsilon 2 minus epsilon, and your this magenta line, which is the E bound, is basically D max over square root 2k minus 1. Yeah, So you can see that by choosing epsilon and k, of course, you can modulate these a little bit, but the basic idea is there is a residual set in both. So you can see that you can never go unbounded here. The idea is you will never go unbounded. Why? Earlier you had some v dot negative semi-definite only in terms of the e dynamics. Now what happened in terms of the e variable? Now I have a residual set. I have sort of this v dot negative semi-definite condition for both. It's an and condition. It is an and. It's not an or. It's not one or the other. So if even one of them, if a tilde, the parameters try to escape this bound, right? If the parameters try to escape this bound, your v dot will again become negative and pull them back, right? And similarly, if only e starts to escape the bound, then also you will be pulled back by the negative v dot. So you move out in any direction, it doesn't matter, you will be pulled back out. So therefore both e and a tilde will remain bounded. So you see, and there's an and condition in the residual set. So this is the rather nice feature of the sigma modification, that first of all, it looks very simple compared to projection. Yeah, all of you have to agree, we all like simple things. Yeah, so all we did was really just add a damping term, which would have sounded very, very logically obvious to all of you, right? I mean, and hence, when Kokotevich came up with it in 1983, right? Really, really, really far back. That was the logical conclusion. The absence of the damping term was doing some bad things, was essentially killing the robustness. So obviously, this is a very, very intuitive answer. Add a damping term. So in the presence of disturbance, you have very nice performance. In the sense, you have bounded performance. And if I increase my k, I can, of course, reduce my residual set, right? Uh, Epsilon is, of course, the point is epsilon is, of course, bounded, right? So if it doesn't matter what you cannot do too much with this bound, is what I'm trying to say. You cannot do really too much with this bound. Okay, and we'll see why. Yeah. uh, and why we cannot do too much, I mean, one obvious reason why nothing much can be done is look at how the expression looks, right? It is epsilon times 2 minus epsilon, and epsilon is the choice of epsilon is just between 0 and 2, right? So whatever you do here, the maximum value is rather bounded, right? I mean, it is lying, epsilon is between 0 and 2. So if you choose epsilon to be very close to 2, then you have some really small quantity here. I mean, the way to make this small is to make this large, right? So the largest this value can take is not much, honestly speaking. I mean, in fact, um, I don't. Yeah, we have to see. It's essentially not difficult to compute what would be the largest value this guy can take. So this is 2 epsilon minus epsilon squared. So if I take partial with respect to epsilon, this will be 2 minus 2 epsilon. So at epsilon equal to 1, you have an optimum. And what is that? And this is, so essentially the denominator is equal to 1 at epsilon equal to 1, right? So that's what the denominator is, exactly equal to 1. Right. Now the question is this the maximum value? Yes, because if I take second derivative of this guy, so another derivative, it's minus 2. It's negative 2. Therefore, this is in fact a maximum. So the largest value this can take is 1. Right. So the idea is that the residual set, yeah. So the minimum, so it looks like from this, the residual set, the maximum or whatever, the least you can make this is A, which means your error will be less than A. Okay, and not smaller than that. Yeah. So if your true value is A, you will be at 2A or minus 2, 2A or 0. Okay? Because your minimum error is A. A tilde is the error in the parameter estimate, remember. Yeah. So your parameter estimation error is A, which means if the true value is A, then you are either at 2A or 0, which is not saying much, right? So the residual set is large. On the other hand, the parameter residual can be made really small by choosing large control gain. That is still there. But in any case, we are getting bounded performance, all the cool things. So we should not be complaining too much, I guess. However, one of the two things. First thing is, even if the the disturbance is 0, you still get only bounded performance. Why is that? Suppose I put d equal to 0 in everything, then what happens? This d max term is what goes away. This half goes away and the d max goes away. All of this goes away. Okay, so this is not there, this is not there. It doesn't matter if this is there or not, it's just some scaling. But this term goes away. Now if this term goes away, what changes? I still have some term here, some residual term here, yeah, some disturbance like term here because of my introduction of the damping. So my introduction of the damping creates a disturbance like term, which is not going to go away even if you kill the external disturbance. Yeah, so you can also think of A as some internal disturbance, this damping as some internal disturbance. That's what it behaves like, right? So this term is not going anywhere. So all that will happen is that this will be not there, this will be, zero. This term, you can go to zero, but you will still have a bound here. Yeah, and if you have a bound, then you will still get boundedness. Yeah, E will still not necessarily go to zero because you have some kind of a residual, additional term here. Yeah, because even if this term goes missing, yeah, you still have this guy. Yeah, and you can see this is like a disturbance term, and this is not going to allow V to go to zero even in the absence of disturbance. So what happened? The sigma modification did not need knowledge of the bounds on the parameter, but of course it can't do everything, right? There's always a give and take in life, right? This is the important lesson. Whenever you see a very technical presentation where there are no assumptions and everything can be done, be very, very skeptical. Yeah, because there is no free lunch. Yeah, so we did not require knowledge of parameter bounds, and the construction was rather simple. But uh, even in the absence of disturbance, it's only going to give bounded performance. If you're happy with that, great. If you're not, then you want to use projection. Yeah, the final thing is, when E is really small, um, when E becomes really small, you have poor tracking performance. Why? Okay, when E becomes really small, this guy goes to zero almost, right? This guy goes to zero. So what happens? You just have this damping term which is going to push the parameter value to zero, right? Because it's just exponential decay, right? So this is going to push the parameter value to zero, right? And it's, I mean, if you've learned the value of the parameter, suppose you're getting very close to the true value of the parameter, yeah, and then suddenly your errors became zero in the system, then you are essentially going to unlearn what you just learned. Yeah, you learned the value of the parameter after significant effort, I hope, but you're going to unlearn it. Yeah, because of this kind of a property. So in order to resolve this second issue, the first issue cannot be resolved. Yeah, doesn't matter. If you'll always get only bounded performance with these kind of modifications where you don't have any projection. But for the second issue, you can do some nice things, right? So if and that is called the epsilon modification. It came 4 years after the sigma modification by two other big names in adaptive control, Narendra and Annaswamy, right? And what they do is very simple. Again, I mean, very, very intuitive and nice, simple results. That's the best part of these. Instead of having just a sigma here, yeah, they put a term which is dependent on the parameter error, okay, and an absolute value. Okay, so this is not exactly smooth. Yeah, not exactly smooth. So they put an absolute value here of error instead of the sigma. That this is called the epsilon modification. How does it change things? As usual, you have the same, Lyapunov candidate, have the same cancellations, okay, and you are left with the same sort of terms here, right? The only difference is instead of the sigma appearing in these terms, the absolute value of E appears here. Okay, doesn't change anything because this is non-negative. Yeah, this is important. Absolute value is important, okay, because otherwise uh, you know you could have negative quantities. Yeah? So just to ensure that these are non-negative quantities, this is important, right? So you have an absolute value of E here because sigma, if you notice, was a positive gain, right? So obviously if you want a damping term which is a negative term, this has to be positive, right? Can't have arbitrary sign quantities here. To ensure that that it's at least not negative, you have to put an absolute value here, right? Otherwise, this is not a damping term. It can be a blowing up term also, right? So therefore, the absolute value E is very essential here, very critical. So all that this does is it changes here. Okay. Instead of sigma, you have an absolute value of E here. And then, rest of it is pretty much exactly the same. Yeah. And in fact, the residual set expressions also turn out to be exactly the same, because nothing changes except for this sigma being replaced by this absolute value of E here. Right? This has the same issue, of course. It is still only uniformly ultimately bounded if D is equal to 0. Why we call it uniform ultimate boundedness? It is uniformly bounded because initial conditions don't impact the bound, right? You will still reach the same residual set. You see there is no initial conditions appearing here. That's why it's uniform. Why is it ultimate bound? Because it ultimately goes to this. That is, it may start outside, but it eventually goes into this set. Yeah, that is, asymptotically it goes into this set. Yeah, not necessarily in one step or anything like that. Therefore, it's uniform ultimate boundedness. Yeah, if you look at large time, it is uniformly bounded. So this bound is not impacted by the initial condition, but is valid after large time, right? So now what is the difference that happens here is in the adaptation law. Notice what happens. Earlier, the issue was that when E became small, this term has no impact, right? And this term pushes A hat to 0 and leads to unlearning. Okay. Now, what did Annaswamy and Narendra do? They did the smart thing, put an absolute value of E here, and could not have put E here, so they had to put an absolute value, right? And what this does is when E gets close to 0, both terms are equally small. So there is no unlearning. Yeah. If A had reached close to the true value of A, then you continue to remain close to it, because the right hand side of the derivative is small, because E is small, so derivative is small. So obviously you're not moving too far away from the well learned value. Therefore, your tracking performance is going to be better. Okay, that's the whole idea of epsilon modification, which is sort of a one can say an improvement over the sigma modification. Remember, although that you did put in a non-smooth term in the update law. Yeah, many um, theoreticians and maybe even applied engineers may not like this. This is a high frequency term in some sense, right? Because if your E is oscillating between negative and positive values around the origin, then this is sort of giving you some trouble. Can potentially give you some trouble, yeah, because of the sign. Yeah, this could become plus minus and all that. Yeah. So remember that this may not always be the best option, but well, whatever. I mean, this is what is the epsilon modification. Yeah, one can also smoothen this, I guess, if you want. Yeah, but that's on you. Yeah, that's also a possibility, right? A smoother version of this is also possible. Yeah, you can again use tan hyperbolic or sigmoidal type functions. All right, excellent. So, what did we see today? We looked at an alternate way of doing robustness or imparting robustness to adaptive controllers via the sigma and epsilon modification. The idea is that uh, the lapse or the flaw in the earlier design is the absence of a damping term. So both sigma and epsilon modifications add a damping term to the update law, adaptive update law, right? While in sigma modification, it's a constant sigma gain in the damping term. In the epsilon modification, it's the gain is actually absolute value of the error, right? The advantage of epsilon modification is that when the parameter has been learned and the error goes close to 0, then the sigma modification will lead to unlearning of the parameter, and a hat will become also 0 because of the damping term. But in the epsilon modification, because of the absolute value E scaling, your parameter value will not be unlearned in spite of the fact that your error goes close to 0. Okay? That's the advantage. In both these cases, there is a give and take because the bounds are not used. Like in the projection case, you get only bounded performance even if your disturbance is zero. Okay, so there is, of course, like I said, a give and take involved here. All right, excellent. So I hope you found this week rather interesting and learned a little bit about robustness in adaptive control. So I will see you in the upcoming week's sessions. Thank you.